In this video, we look at the geometric series. Sometimes I think Red Pen, Blue Pen calls it the best friend. and I love his videos. For this video, we're going to prove that it does converge under certain conditions, but it turns out to whether it converges or not depends upon whether a specific sequence of numbers converges. Remember, a sequence of numbers is just a sequence of numbers, but a series is you add up those sequences of numbers. And so we need two background videos: monotone sequences of real numbers and subsequences of real numbers. So let's prove the theorem on sequences first, and then we'll get to the geometric series. And what the theorem we want to prove here is this: that if we have a number between 0 and 1, and we look at this sequence, it converges to 0. If it's greater than 1, it diverges, but in here it converges to 0, diverges if less than or equal to -1. If it's 1, it converges to 1 because every number in the sequence is 1, and 0 converges to 0. So let's prove number 1 first. So first we want to show it's a decreasing sequence, and we do that by the ratio. We look at the ratio of the terms, and if this just is equal to A, but we said A was between 0 and 1, so it's less than 1. So this is a decreasing sequence. So this sequence is bounded below by 0, and you can see that by, A has to be greater than 0. And then if we multiply both sides by A, we get 0, A squared is bigger than 0. And we can do that for all n. So for all n, it's strictly greater than 0. So by background video 1, that we have a monotone convergent sequence that's bounded below, monotone decreasing sequence that's bounded below, then we know that the sequence converges. Okay, we don't know what it converges to just yet. So let's assume it converges to some number L, and that's the limit of this sequence. So let's create a subsequence, A plus 1. And we can pick any sequence, but we're just, instead of starting at 1 and then go to 2, then, A1, A squared, A3, we're going to start at A squared and then go to, so it's almost like the same sequence, but the first term is different. So it's technically a subsequence. Now, background video 2, we know that since this is a convergent sequence, every subsequence converges to the same value. So note, let's look at this subsequence. So we know it converges to L, but this limit is the same as A times A raised to the n. And since there's no n in this, we can bring it out front. But we said this sequence, the original sequence, converges to L. So we have L is equal to A times L. And the only way that can happen when A is between 0 and 1 is that if L is 0. So that says the sequence converges to 0. So number 1 is finished. Now number 2, we want to assume that A is greater than 1. So this is shouldn't be 0, it should be 1. Then if we look to determine if it's increasing or decreasing, we can look at the ratio. This ratio is A, which is greater than 0, which says that it's a monotone increasing sequence. So this sequence is increasing. Now we're going to prove this by contradiction. Okay. Oh, and here's another point, that if we look at this, we're starting out with A strictly greater than 1. So it's bounded below by 1. All right. And we know it's increasing, but we don't know if it has an upper bound or not. But we're going to assume that it does have a limit and call it L. Now we want to create a subsequence again, A to the n plus 1. And since this is a convergent sequence, we know that the subsequence converges to the same value. And then we do the same trick of L is equal to this limit, but which is the same as this. But this limit was L. And so we have L equal to A plus L, and these are A is strictly positive, above 1. So that implies that L has to be 0 for this to be true. But that's a contradiction because we said A is strictly greater than 1. So it can't be, you know, it can't go to 0, can't limit below that. So the sequence does not converge, it diverges. Okay. Now 3 and 4 are proved similarly, so I'm going to let you do that on your own to keep the video at a nice length. 4 and 5 trivially converge. If you plug in 1 or 0 for all values, then it's trivially converges to itself. So now let's look at the geometric series, which is defined like this: A plus A times R plus A times R squared, etc. Now if A is 0, then this series trivially converges to 0 because each term is 0, and you know it's 0. So we have to assume that A is not 0, and we're going to assume that R is strictly less than 1. Then we're claiming that the series converges to A over 1 minus R. If A is not 0 and it's greater than or equal to 1, then the series diverges. So the proof of this is this. So if it's trivial if A equals 0, because then all these terms are 0 and it converges to 0. So now let's assume it's not 0. So let's let Sn be this partial sum. There's n terms, and that's where that n comes into play. Now if we multiply R to both sides, we get this, R times Sn, and then this. Now if we subtract the two, so S minus RS, we get this, and then you can factor out an Sn to both sides. Okay, but if we were to just look at the terms and take this minus that, we end up with this. You know, the A doesn't cancel and this A R raised to the n. So we get this. Now we can divide both sides by R, assuming R is not 1. And we get this. So Sn is equal to this quantity here for R equal to 1. Now, so to know whether the geometric series converges is simply whether this converges or not. And this is a sequence of real numbers. And notice that the only term in here that has an n that changes is this R raised to the n. So these constants can be brought out front, and we have 1 minus R to the n. Well, from theorem 1, Sn converges when R is less, the absolute value of R is less than or equal to 1, and diverges otherwise, right? Because whether this converges is simply based on this. So if this blows up to infinity, the whole thing doesn't converge. If it converges, then this whole thing converges. And so anyway, so that's the proof of the geometric series. I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.